let's continue on the introduction to the gear. Okay. This is what we did in the last lecture. We went over some terminologies of the gear. Okay, so this diagram we filled out already. All right. Yeah. Let's keep going here. So we have another diagram here to fill out. Okay. Now you have the handouts. You can use the handouts to So what I'm trying to let you get used to is to get used to all the terminologies, okay? And particularly it will be helpful when you try to create the gear using SolidWorks here, okay? Yeah. Now, when you create the gear, the whole idea behind creating it is creating a whole cluster of circles, essentially. All right. As you can see, there is a pinion on the top and the gear at the bottom here. So they are mating together, and the circles are pretty much basically a pair. So as you can see, first circle is this dashed line here. Okay, this dashed line. Okay, which is this arrow pointing to these two arrows. Okay. Now these two circles, they are called base circle. Okay, base circle. This is a very important circle. Base circle is the circle where the so-called involute profile will be generated, as I'm going to show you shortly. All right. Yeah. So basically, you can see starting from the base circle. Okay, this is the base circle here, and this is the portion of the gear profile, right? That portion of the gear profile is called involute curve, and that curve starting from the base circle. Okay, yeah. Same thing for the other side here, right? Base circle. And the top circle, which is this circle here, as we know that this circle, where is the arrow pointing? Which arrow points the arrow to the circle? Oh, there's a too small one here. Remember what this circle is? This is called, yeah, addendum circle, right? Okay, addendum circle. Okay. Yeah. And the bottom two circles, which is these two arrows pointing to. Okay. This is the dedendum circle. Okay. Yeah. It's dedendum circle. So now you have basically an idea here is this. You connect the two origins of the pinion and the gear. Okay. Yeah. Then each one of the pinion and the gear, as you can see, the two solid circle. Okay, there's two solid circle here. They're tangent to each other, and that two arrow. Did we point that two arrow? There's no arrow. So remember, what are these two? This is the two called what? The peach circles, right? The two solid ones. Okay, these are the peach circles. Okay. Yeah. Two arrows on the right. Oh, here, right here. Yeah. Okay, the peach circles. Okay, yeah. And there is a line CD over here. So this line CD. Okay, this line CD here. That line CD is called line of action. Okay, this is called line of action. Okay. So line of action, essentially, this line here is the action-reaction force direction. So this pinion teeth will push the gear teeth, right? And the force being pushed or being reacted is along this line of reaction CD. Okay? And the line CD intersect the O1, O2 at this point P. And that point P is called peach point. Okay? It's a particular point called the peach point. And that's basically the tangent point between the two peach circle. Okay, so this P here is called peach point. So whenever you have two surfaces, and the surfaces are tangent to each other, and that tangential point, that's the pitch point. Why is it called this pitch point in this particular cases? Because they are involute. I'm going to show you. The two pitch circle, they always tangent here, and the line of reaction always intersect the pitch point P. And actually, in terms of the gear, there's only one line of reaction, which is always this CD. Okay, so basically, as the gear moves, okay, I'll show you that. Maybe I'll show you here. As the gear moves, I'll use animation to demonstrate the idea here. So this is a commercial software called Gear380. It's quite good in terms of generating a gear for you. Okay, so the screen size is a bit of a didn't expect that to happen. Yep. Okay, so I think for people in the back, it's hard to see, right? Unfortunately, I can't move it up anymore. Okay, but what you can do is, when it's moving, okay, when it's moving, for people observe the contact point between a pair of two teeth. Okay, observe the contact point of a pair of two teeth. That contact point, okay, this contact point always moves along this line of reaction. Okay, always moves along line of reaction. So if you observe carefully there, you see that the line of contact point between two teeth, okay, they always move along this line of reaction, that straight line, okay, the one that indicated by the yellow and the red dots there. Okay, so right here they basically get away from each other, right? Yeah. So the contact point always along the same line of action. Okay, when you use the involute profile, that's the idea. Okay, yeah, is that okay? And there is an angle between the line of action and the horizontal line here. Okay, so the horizontal line is basically the tangent line between the two pitch circles. The angle between these two is called phi. It's called the pressure angle. Okay, pressure angle. Okay, so pressure angle generally in the gear usually 20 degree or 25, or there's opposite angle 14.5 degree. Okay, and that's actually something like how the force, the direction force, is being applied, right, from the pinion to the gear. Okay, yeah. So if I use the geometry at here, this is the line of reaction. The line of a reaction or line of action, as you can see, it is tangent. Can you see that? It's tangent to the two base circles. Okay, if you look carefully here, the line of action is tangent to the two base circles. It's like this. You have two circles, right? These are two base circles. Then you draw a line of action. Okay, that two, the circle, they are tangent to this line of action. Okay, yeah. So tangent basically means from the origin of the circle, you can connect the tangent point, and guess what? Geometry-wise, it's 90 degree, right? Same thing at here, and 90 degree. Okay, 90 degree. Okay, yeah. So this right triangle, okay, if you use your geometry here, so this triangle, this angle here will be the same as the pressure angle phi. Okay, same thing at here, the pressure angle phi. Okay, yeah. So then, if O1 up to point P, the O1 up to point P represent is the radius of which circle? Radius of this circle, right? And which circle is this again? Pitch circle. So if this is the pitch circle radius, let's say I'll use RP. This is the pinning, right? So RP represent the radius of the pitch circle, and here I can use RG represent the radius of the gear, the pitch circle. Then this radius from here to here represent which radius? It's the radius of which circle? It's the radius of the base circle here, right? So this is RBP. This is RBG. Let's say radius of the base circle for the pinion and the gear. So what is the connection between the base circle radius and the pitch circle radius now? This is the right triangle, right? This is the right triangle here. So very simply you can put it is what? The RBP equal to what? RP times cos phi. Or RBG equal to RG times cosine phi. Okay? Yeah. Now that's a very important connection. The base circle radius and the pitch circle radius. Okay? Yeah. Because remember in the previous lecture I said pitch circle is an important circle because every other calculation are based on the pitch circle. Right? Yeah. So you always start with what is the diametral pitch? Right? You always start with diametral pitch. And what is the number for teeth? Okay? What is the number of teeth? Okay. So then the diametral pitch equal to N over D, right? N over D. So given the number of teeth and the diametral pitch, you will be able to calculate the number of teeth. Okay? That was you'll be able to calculate the pitch diameter. Okay? Once you have the pitch diameter for the pitch circle, guess what? You will be able to calculate the base circle diameter, right? Once you have the base circle diameter, as we're going to show you, you'll be able to create the involute profile. Okay? And from there, all the gears will be able to generate it. Okay? Yeah. Okay. So, and I think that's all the terminologies on this line right here. Okay. The other thing I need to point out is, so if you look at the gear profile, the portion of profile between base circle and the addendum, this profile, this portion. Remember what do I call it? This portion profile, I call it what? Involute, right? The portion of profile between the addendum and the base circle, this portion, okay, this portion here, okay, that is not involute, okay, that's not involute. So when you generate the gear, this portion here, what we generally do is it's a straight line. So we draw a straight line from that location up to the origin here, okay. So the starting point, it's a straight line. It's not a curve, okay. Then you can create a fillet, okay, at that location. Okay, you know what I'm saying? Yeah. So that's the portion of profile within the addendum and the base circle. In the next week tutorial, the video you're gonna go through, okay, is to create the gear profile. Okay, that's the case. Basically, you do this. Okay. However, okay, it's a bit too early to say, but you know it's okay. So the base circle in this case has to be above the addendum circle, right? Okay. Then I can draw a straight line, and I say this is basically the straight proportion between these two circles. Okay. Yeah. Now there is a situation, particularly when the number of teeth start to increase pretty large. Okay. Then, as we're going to learn, that base circle will start to shrink. Okay. It'll be basically below this addendum circle. If the base circle is below here, okay, and actually guess what? the whole profile of the gear is going to be involute. Okay, it's not the whole thing gonna be involute. Okay, so you don't really need to create that straight line anymore. Okay, so there is a little subtle here, but the video I created didn't take that into consideration. So just heads up here. Okay, so that's the terminology for this picture here. Okay. Any questions? Okay, all good. So let's move on. Okay, now let's look at some details now. Okay, so this probably should come first regarding the gear tooth profile. But anyway, for people who learned kinematics and you learned one particular mechanical component, it's called cam, right? Yeah. And what does that do is basically, not just a cam and maybe some other profile. So let's say you have two things, fixed at two points, and then you want to make the two things contact each other and drive each other, something like that, right? Yeah. And what you want is you want to make sure that the transformation of the angular velocity is a constant. So basically you want omega 1 over omega 2 equal to a constant. And that's actually what we really want for a gear, right? You want to have a constant angular velocity ratio between the pinion and the gear transformation. Okay? Yeah. Now, this is not a gear. This is just arbitrary two surfaces. You actually can't achieve this constant angular velocity ratio. You can't. How do you do that then? You have to make sure that the two profile, okay, the two profile, they are called conjugate. Okay, you need to have two conjugate surfaces basically in order to achieve this constant angular velocity ratio. So what does the conjugate surface mean then? So conjugate surface. So conjugate surface basically means this. Again, you have this line of action, right? So that line of action is actually basically perpendicular to the surface, right? Normal to the surface. Okay? Yeah. In order to have this constant angular velocity ratio, the line of action has to pass the same point P. Okay? Just like the gear that we just draw there. Has to pass the same point P. However, if it's not involute, if it's some other conjugate surface, you don't really need to have a unique line of action. So at this moment, maybe this is the line of action. At the next moment, you have another line of action, but it also has to pass the same point P. You know what I'm saying, right? And that's one type of this called a conjugate surface. Now, when it comes to the involute surface, as what I showed you there, the line of action doesn't change, right? It's always the same one, and it always passes through the point P. Okay, so involute one is a little bit more special one as a conjugate surfaces. Make sense? Okay, yeah. So the working nature behind that is a little out of scope of this lecture, but you should just know that basically the facts. Okay, the involute profile essentially is conjugate surface. What does it guarantee? It guarantees that you will have a constant angular velocity ratio. All right? Yeah, that's the basic idea. Okay. Yeah. Okay, so now coming back to the gear tooth profile. Yeah. What is what? Sorry. Oh, involute. Okay. So here, this is the involute. So, what's the meaning of the involute? I guess involute is very much like a convolution. So look at this curve here, right? So imagine you have a piece of cord or thread wrapped around this cylinder here, all right? So now what you're going to do is this. You pick the one end of the thread, okay? Make sure you put it very tightly, okay? And then you start to unwrap that thread, okay, from this cylinder, all right? Yeah. So this action of unwrapping it, if you draw a curve trajectory, of this tip of the thread, you will be able to generate this so-called involute curve. Okay, so it's a sort of an unwrapping procedure, right? Yeah. Frankly, I'm not quite sure what does involute mean actually. Is it sort of wrapping things? No. Anyway, was that clear? Right. So the curve here, this curve is the involute curve, right? Yeah. You can unwrap it on this side here. That's fine, right? You can unwrap, doesn't matter, right? But imagine this, right? Let's say I am unwrapping it from A0 location. Then how much did we unwrap from here? This portion. See this portion of arc. Okay. Look at this A0 B1. That portion of arc is unwrapped very tightly. So A0 B1 will become what? From the picture will become what? A1 B1, right? Will become A1 B1. Okay? So basically the length of A1 B1 will be the same as the arc length of A0 B1. A1 B1, because you're wrapping very tightly, so A1 B1 will be tangent to this circle or the cylinder. So that's why this is 90 degree at here, right? Yeah. And you can keep doing this process for the next few points, and then you connect all the points, you get the involute curve. And actually, there's just lots of YouTube videos to how they use the method they used to generate the involute curve. So they essentially create whole bunch of tangent lines, okay, and then they connect all the points, give you the involute. But that's not accurate, right? That's more of an approximate. Now, what we want is we want a more accurate version of involute profile. So what do? We make use of the mathematical knowledge of a so-called parametric equation to generate this involute profile. So this is basically, I'm going to skip the procedure of deriving it, but I'll show you what it is though. So let's say I have a circle. Okay, I have a circle here. I'm going to generate an involute profile. Let's say I'm going to start it from this A location to generate involute profile. The profile I'm going to generate, let's say, is to that direction. Okay? Yeah. So what does that mean? That means basically imagine there's a thread at it here. You're going to start to unwrap the thread, right? Let's see, how much did we unwrap? Maybe from here to here we unwrap this portion. And how much distance do we go? That's t. Let's see, we use a parameter t to represent. So this much is unwrapped. Then in terms of the traveling, so that point will go to somewhere here, and this is 90 degree. Okay, it's 90 degree. So essentially, you track the location of this point, right? That's the parametric equation. Was that good? Yeah. And if the radius of the circle is r, okay, the radius of the circle is r, then the trajectory of this involute curve is this. The x equal to r cosine t plus rt, okay, sine t, and y equal to r sine t minus rt, okay, cosine t. Okay, it's a parametric equation in terms of parameter t. You plug in different t, you get a different location of the curve. Okay, is that good? If you want to know how this is derived, in the lecture notes, there's pretty detailed derivations there. Okay, yeah. So based on this equation, we actually can extend our knowledge a bit of more here. Let's say if I say, okay, I want my involute curve to start from here. Okay, start from this B location. Okay, then what will be the parametric equation for our involute curve starting at the B location then? So for B location, what's the difference now between A and B? The only difference is it's a 90 degree starting difference, right? It's just a 90 degree starting difference. Then the parametric equation for the B location, all you need to do is basically you change the t to t plus pi. Okay? Just change the t to t plus pi. However, you don't change this t though. You only change the t inside the sine and cosine. Okay? So okay. In the next week tutorial, you will see another case, which is the case I used in terms of generating the gear. So what if I really want the profile to go this way? Okay, then what do we do? In this case, basically, if you think of the point, when the point going this way, the point is like going counterclockwise, right? That's positive. If it goes this way, you can consider it's unwrapping in this direction. It's clockwise unwrapping. And actually, the only thing you need to do is, when it go this way, you need to change the t to the negative t. Okay, that's the point. Okay. So anyway, watch out for the next week tutorial there. Okay. So that's Involute profile. In the CAD software, if you have the diametral pitch, you have the number of t's, then we have the pitch circle. Then based on the relationship of a cosine and relationship, you can find the base circle. Once you have the base circle, in the CAD software, you generally can enter the parametric equation like this. Then you can create the Involute profile. You create two Involute profile, one this way, one this way. Okay, then we'll be able to create the gear. All right, so that's all. It's all there. Okay, so the next topic is pressure angle, point of contact, line of action. So I actually talked about this a little bit already. Okay, yeah. Point of contact, basically what I'm talking about is the contact point between two pair of teeth. Okay. As the animation, as that the software showed you there, so when the gear and the pinion started to move, that point of contact, okay, this contact point here, will always travel along this line of action. Okay, always on the line of action. So that's point of contact. And when it comes to this particular point, this guy here, that's the intersection between the center to center distance and the tangential point between the two pitch circle. So that's a particular one, the point of contact. This point is what we call it, the pitch point, right? Pitch point. Okay. And pressure angle is angle, basically the line of action here. Okay, line of action. So if I use the Involute curve as a demonstration pressure angle. So for example, right, this is the base circle, and this is the Involute curve generated from the base circle here. So what is the pressure angle then? So pressure angle essentially, if you draw a tangent curve, okay, to the base circle, okay, to the base circle, then the intersection between the tangent line and the vertical line here, okay, and then you can get the pressure angle right here, okay, or this angle, okay, or this angle, okay. So then theoretically, right? So theoretically, when you create a gear, you can use any kind of pressure angle. It all depends on what? All depends on how you draw this tangent line. If you draw the tangent line here, it's one pressure angle. If you draw the tangent line there, right, you get another pressure angle. Okay, yeah. But generally, we use that 20, 25, or 14.5, which is obsolete. Okay, so 20 is what we mostly used here. So this is a 20 degree, for example. Okay, this is a pressure angle, and this is two base circle. Okay, right? Then you can actually always imagine within these 2 points. Okay, within the 2 points, there's always a pair of teeth coming in contact into each other. Then how do we let's say picture the contact, the two teeth then? So all you need to do is, if this is the contact point, and I can start from the base circle and draw a involute curve, portion of involute curve, and starting from the other side and draw another one, and that's basically the contact point between the two curves, right? The involute curves. Okay, yeah. So, all right. So that's a pressure angle there. Okay, so one more thing here, contact ratio. Okay, contact ratio. Before we talk about contact ratio, okay, let's observe one of the thing at here. This thing is so small here. Okay, so maybe I'll just come back here. So the question here is this: where is, if you have a pinion trying to push the gear, where is the starting engage point? Okay, where's the starting point for the pinion to engage the gear? And where is the location for the pinion to depart from the gear? Right? You see what I'm saying? So basically, you have a T set here from the pinion. So it started to move, rotate, and all of a sudden, right, it started to engage with the gear now, right? And then start to move again. At a certain point, this teeth, right, this tooth will start to disengage from the other one, right? Yeah. So the question is, what is the limit? So where does it start to engage, and where does it basically start to disengage? Okay. And also bear in mind, the contact point between the two teeth is always on what? It's always on the line of action, right? It's always on the line of action. Okay. So see here, this is the line of action. Okay, it's line of action or pressure line, right? So where does it start to engage with the other part of the gear? Okay, the other pair. Think about this, right? This curve here. This curve is the addendum circle. So what does the addendum circle represent again? It represents basically the limit, right? It represents the limit where the teeth, basically the surface is, right? The surface is, okay? And the addendum circle at here, okay, will intersect, okay, this circle, let's see, is the base circle here, okay? So the addendum circle of the gear will intersect the base circle of the pinion. Okay, so you had to use your mind here. The addendum circle will intersect the base circle of the pinion, and that intersection point is the location where the engagement started to happen. Okay? And the addendum circle of the pinion will intersect the base circle of the gear. That intersection, which is this B location here, is the location where the disengagement happens. Okay? So on my computer, it actually looks fine because a portion of this is gone here. So, but I guess we can still see here, right? So you look at this. Look at the yellow dot at the bottom of the screen. The yellow dot at the bottom of the screen here. Okay? If you can stand up, you can see the yellow dot at the bottom of the screen here. Okay? That black line here, and this one here, is the addendum circle of the top one to the gear. Right? Okay? And this blue color, this guy here, is the base circle of the pinion. So as you can see, basically the engagement is right here. Okay, it's right here. And as it moves, moving to this point here, that's the intersection between the addendum of the addendum circle of the pinion and what? The base circle of this gear. And that's where this pair of these two T's will disengage. Okay, will disengage. So the point of contact between the pair of T's travels the distance from this yellow dot to this yellow dot, right? Travel this much distance. Okay. Or in other words, that's how much contact length it gone through for the contact point. Okay, contact point. So this is basically where the contact ratio comes into the picture. Okay, the contact ratio is basically about the distance between the two yellow dots. Okay, two yellow dots. So if I go back to my diagram here, okay, so the distance AB, okay, we use LAB, okay, represent is the contact length, okay, the contact length. Yeah. Then the contact ratio, okay, the contact ratio is defined as this. So contact ratio, we use MC to represent the contact ratio, and contact ratio is MC equal to LAB over PB, okay, over PB. PB is the circular pitch along the base circle. So this is small p, huh? This is supposed to be small p here. This is the circular pitch of base circle. Okay, that's how the contact ratio is defined. So what is circular pitch of the base circle? I'll show you a diagram here. Now remember in the previous lecture, we have a so-called circular pitch, right? Small p. But that's the circular pitch along the pitch circle. So this is the pitch circle. So when you measure the arc length from here to here, that is the circular pitch along the pitch circle. We use small p, right? We use small p for this portion. But if you do the same thing, if you measure the arc length along the base circle, we get that the circular pitch along the base circle PB. Okay? Yeah. And the ratio between this contact lengths LAB and PB is the contact ratio. Alright? Yeah. And there is an alternative way of calculating MC, which is based on the diagram at here, which is based on this so-called QT over P. So what is QT then? If you look at the diagram here, this is the starting the moment start to engage. This is the moment when it started to disengage. Then there is this so-called arc approach, arcaphoresis. But overall, that QT is basically the QA plus QR. So okay, so basically from here to here, this portion for arc length, that's QT. Okay, and the P, remember what a P is? Small p. That's the circular pitch on pitch circle. Okay, on pitch circle. That's contact ratio, right? So either way, you can calculate this or that. And why they are the same? Look at my lecture notes. Okay, there are 2 or 3 pages of a drawing showing why they are the same thing. Okay, yeah. Was that good? So in terms of calculation, right? PB is actually pretty easy to obtain. Okay, the PB is related to this small p. So basically, the circular pitch of the base circle is related to the circular pitch of pitch circle. That PB equal to P times cosine phi. And phi is the pressure angle, right? Phi is pressure angle. Okay. Circular pitch small p, if you recall from a previous lecture, What is the circular pitch of small p? Small p is what? Small p equal to pi over the capital P diametral pitch, right? Diametral pitch. So that can be calculated. So once you have that, you can get the circular pitch P, you can get the PB. And once you get the PB, you only need to calculate LAB. And the LAB, geometrically, you can see in the lecture notes how it's derived, which is this guy here. Okay? This guy. So you don't need to memorize this, okay? There is actually really no point in memorizing this. But the symbols used here, they are essentially just radius of the addendum circle, radius of the gear addendum circle, base circle, all of these things here. Okay, so just carefully, okay, you'll be able to get the LAB right. Okay, is that okay? So what does what does contact ratio tell us? In the early stage, okay, in the early stage when the design is not that perfect, so generally you only have every time you only have one pair of teeth coming in contact with each other. So that basically actually means the gear teeth, the ratio is just 1. Okay, but now you want the load to be carried by a bit of a more pair of teeth. Okay, so that you have a higher capacity for carrying the load, or sharing the load at least, right? So you really want is this MC value, okay, to be greater than 1. So in general, you want it to be greater than 1.2. Okay, that's the contact ratio. Okay. Okay, so that's contact ratio. Any questions? Yeah. My requirements for you is, you know this, how to calculate this, right? And you know that you have to calculate this, okay? And you know where the PB is from. That's enough. Okay. And the last concept, okay, is interference. Okay, interference. This is a pretty interesting concept too. Interference basically means, in short, right? It basically means when involute portion get in contact with non-involute portion, you have interference. All right, so that's basically the concept of interference. So let me write it down. Let me write down here. Okay. Okay, non-involute profile. So, take the gear as the case. Where's the involute portion? It starts from where? Starts from base circle, right? And where is the non-involute portion? It's between the base circle and the addendum circle. So then, the occurrence of interference basically means if there's any chance that, let's say, for example, this gear part involute started to engage into this non-involute portion, right? Then you have this interference. Okay, that's what happens. Yeah. So under what condition will this interference happens then, right? Yeah. So here's a few facts that you have to understand this here. Okay. One fact is what I just said previously. The starting point, the point of that started to engage, and the point when it started to disengage, right? Or started to leave each other. And this is AB, right? Is the distance travels, right? The contact length. Okay. Yeah. So as in this diagram shows here, this capital A, this capital B represent the two moments. One moment is started to engage, the other moment is started to disengage. Okay. The C and the D represent is the tangential. This is basically base circle, okay, and that CD is the a tangential point, right, between the pressure line and the two base circle. Now, if you want to have no interference, the starting point and end point of this engagement has to be within the CD location. If any one of these points is outside these two tangential points C and D, then interference will happen. Okay, will happen. Mathematically, you can prove that, but it's a bit of too much. But I can use this thing to show you. Okay, again, the projector is not showing everything, so which it's a little bit hard to demonstrate. So if I reduce, look at this, right? If I reduce the number of pinion teeth, watch the green dot, okay, and the yellow dot. The yellow dot, okay, the yellow dot is the start and end disengagement points, right? The two green dots are these C and D. Remember what we want? We want the A and B within C and D, right? So basically, in this case, we really want the two yellow dots to be within the two green dots. Okay? Yeah. I wish this is bigger. So, but if I reduce the pinning number of teeth, look at that yellow dot, the bottom here. It started to be outside what? The green dots now, right? The green dots. And that's when you have this interference. So maybe the other gear portion. Let's do this one here. There, right? See that? That one is within this. With this, it's that the yellow dot is outside the green portion, right? Yeah. So basically, as you can see, if I started to move, okay, if I started to move, imagine this location here, this location, okay. So for this location, this portion, this is this pinning portion, this is involute, right? This is involute. Let's give it a little bigger here. Oh, there we go. This portion, this is involute, right? This is involute. But what about this from here to the bottom, this base circle here, from here to here? Remember what this is, this portion. This is not involute. This is actually what? We use a straight line, right? This straight line. So if I move this a little bit more here up to this location, let's say, imagine what happens. If I draw a straight line from here to the center, okay, to the center, okay, from here to here, then that portion, this portion of the involute, is going to actually get in contact with this straight line, right? So if you see, you draw a straight line right here, and guess what? It's going to contact this portion of this involute, right? This is involute. So it's like an orange getting to contact an apple. They don't like each other. So when they don't like each other, the bad thing happens is this orange will try to dig into the apple. So this is when you have this action, you'll hear lots of noise, you know, like teeth grinding each other, right? Then what do we do then? We have to get rid of a portion of material right here, right? That's what we call undercut, okay? Undercut, to avoid interference. But if you have undercut, the consequent effect is you are weakening the root strings, right? The strings of the teeth root. Okay? Actually, when you have a manufacture process called hobbing process, if there is interference, then the cutter basically will automatically remove this the portion of the root, and the undercut will basically happen, right? The interference will naturally be removed. Okay. All right. So any questions? Okay. Thanks.
line to intersect or not?
Which one?
Like for the I'm bad with words, but like for example, there's two gears, right?
Yeah.
So like there's a fillet and this is the sharp part.
Yeah.
So when the gears are moving just like that, for example, if they're not the right size, right? This is bigger and this is like a small piece, right?
Sure.
So if the sharp part like touches the fillet,
Yeah.
is that good design?
Not good.
No, right? That's
No,
not a good
it's-
design. It's a horrible design.
It's horrible.
Okay, okay.
Yeah. So first thing is, when you want to mate the gear, the two things have to be able to mate.
Yeah.
See, mating basically means the two diametrical pitch of the gear and the pinion has to be the same.
Okay.
Right? Yeah. And then the next question is, you want to avoid interference.
Okay.
And avoiding interference, the interference a lot had to do with the number of teeth. So when you have a smaller number of teeth, and chances are you will have the interference. But you can always avoid interference by having this undercut at the root location. But that'll give you this is basically what I just said. You're weakening the teeth, right? You know. But if it's not avoidable, and then if you have to do that, then you have to have this undercut, right?
I was one of the students that missed a midterm
Yeah.
for the break. So
Yeah,
I
yeah.
was wondering what the.
So I have another guy. I'll email you you guys, maybe.
Okay.
Yeah. We'll set up a time sometime. Yeah. Good time for you guys. Yeah.
Yeah, for sure.
Okay.
I just didn't. I wasn't here the last couple of days just because I had some.
Oh yeah.
Some trouble.
Hey, Steven?
No, I'm Nick.
Oh, you're Steven. Sorry.
Yeah, no, I had some troubles getting back from England, so.
Oh, okay.
Yeah.
Yeah. So I'll email you guys and
Okay,
we'll set up a time. Okay.
Thank you.
Yes, I did. But they don't have it with me, and you can come to my office and pick it up. Yeah? Yeah. Okay. Are there already videos on this topic? Video? My video? Yeah. Or other recorded? Yeah, recorded. Yeah. Yeah, this is a pretty hard to explain this concept right here. There's a lot. You know, if you really dig into it, there's 1,000 pages of mathematics behind all these topics, right? You know, some of the conclusions I just said here. So, yeah, I think